Hello everybody, welcome. Today we are going to discuss the solution to the problem sum of square numbers. It's a medium rated problem, but we're going to discuss two solutions to it, both of them based on a couple of observations. The second one would be a more optimized version of the naive approach. Okay, you're given a non-negative integer c and you have to decide, basically true or false, whether there are two integers a and b, integers being positive, negative or 0, such that a squared plus b squared equals to c. So a and b are two variables in your hand and you have to find any possible combination of a and b such that a squared plus b squared is c. Okay, first observation is a mathematical observation that you should always do, always in any sort of these problems. It's realizing the maximum and the minimum possible values of the variables in concern. Let's look at x squared, a general sort of square of a number. What is the minimum possible value it can ever have? Is the value 0 when x is equal to 0? Feel free to try out any other examples if you don't agree with me. Now, was the maximum they could be? It could be tending towards infinity. We don't worry about that. Let's focus on the minimum one and let's set b equals to 0. Just for the sake of convenience, we'll set b equals to 0. Now what happens? We'll look at a squared plus b squared equals to c, where b is equal to 0, which means that a squared equals to c or a equals to the square root of c. This way we have found upper and lower bounds. When b is at its minimum 0, a is at its maximum, the square root of c. Alternatively, if we set a equals to 0 here, we'll get b equals to the square root of c here. Meaning that both of these variables start from 0 and go all the way up till the square root of c. And so we'll get the number n here. Let's put a number n, which is the integer of square root of c. And we'll do plus 1 because of how square root works and how it will take the floor of it when we do the integer. Anyways, now with that in hand, what can we look at now? See, we've figured out the maximum and the minimum possible ranges for both a and b. Was the next obvious step? Enumerate everything. Enumerate all the possible combinations ever. Go for all a in range of n and for all b's in range of n again. And now it's as simple as computing a star a plus b star b is equal to c. If this original condition is satisfied, return true. Now unfortunately, in case you don't find any such possible combinations, you can return false. And that is it. That is the entire solution. One thing we want to also discuss is the space-time complexities. Now the space complexity is rather easy and trivial since we are only ever storing this n variable, which means that the space complexity is in the order of constant time, order of 1. What about time complexities? Look at a range of n and another range of n nested within it, which means that it's going to be order of n squared. But what is n? N can be at maximum the square root of c. So we're looking at the square root of c's square, which is what? The square root of c's squared is just c. So this entire solution runs in the time order of c. Now there's one more optimization we can do. And this is the second observation. First one being, find out the ranges, the minimum and the maximum. The second one is always sort of keep that in the back of your mind. You will find more problems like these which require you to reformulate the problem. And this is the second part of the things. We'll not just look at a squared plus b squared equals to c. We'll just look at b squared equals to c minus a squared. We've just reformulated the problem. This is the exact same equation mathematically speaking. But we've done one very interesting thing. Now b equals to the square root of c minus a squared. What does this mean? Well, this means that b could be anything basically, but look at what the initial conditions were. If you find two integers a and b such that a squared plus b squared equals to c. Alternatively, we'll fix a to be an integer. Let's just fix that. Let's keep this loop as is. But we're going to remove the second loop and we'll ask the question, you know what, let's fix b to the square root of c minus a squared. Is the b the same as the integer of b? Saying that, you know what, we already know a is an integer, but if you find a b is also an integer in the above computation here, this one, if b is also an integer, at that point of time you can say true, return true, because we have found a valid case. And what's the space-time complexity of this? The space complexity remains the same since we're only dealing with one, or in this case two variables now. So it's still constant order of time, but the time complexity now becomes the square root of c. It was square root of c squared, but now it's just the order of square root of c. And this is the amazing thing. Both of these, by the way, observations, the minimum to maximum range one and the reformulating one, are very important to keep in mind. And I've found them more than once in different kind of problems. You can sort of get rid of the last loop, keep the first loop or first couple of loops as is, and reformulate the problem. This, in fact, by the way, is also used in two-sum if you look at the problem in different way. Feel free to check out the video solution to it or other write-ups. The solution for the two-sum relies on this exact observation of reformulating the problem. Anyways, we were able to bring the space-time complexity down to time was now the square root of c, and the space still is order of 1. Anyways, this was a fun little solution to the problem sum of square numbers. If you like this video, let me know. If you dislike this video, do a double thumbs down to really let me know. And if you have any comments, feedbacks or discussions, start them in the comment section below. As always, thanks for watching.